Welcome back to Fluid 2000, and this is the final installment, the final lesson, and I'm just going to take a few minutes to give you an overview of the course and review what we've covered up until this point. And hopefully you will get a chance to practice these skills, because with practicing them comes proficiency. That's the best thing we can do as technicians. So of course, like anything that's a technology or science, it comes with some math onboarded on there. And here we have the formulas that you'll have to be familiar with. And the first one, of course, in the top left-hand corner is Pascal's law, and that's force, pressure, and area, and that has to do with fluids at rest. In the bottom of the left-hand side, you have the volume, rate, time relationships, and gas law in the top right-hand corner, where basically you're looking at the heart and soul of any pneumatic circuit. And in the middle there, we have a little diagram that shows that high pressure, low volume, low pressure, high volume, you're swapping one for the other under Boyle's gas law. And finally, in the bottom right-hand corner, we have Bernoulli's principle, which governs fluid in motion. And that's used quite commonly as well. As we restrict the flow through, the pressure will drop. And as we allow the column to get bigger, the pressure will come back up. So we're changing speed for pressure, which is done quite a lot in fluid power circuits. So which one am I going to choose, hydraulics or pneumatics? Well, that all depends on what I'm looking for to do. Most of the time, your energy source is the same, and the storage device in a hydraulic system is limited to an accumulator, which is a much smaller amount of stored energy than an air receiver in a pneumatic system. A pneumatic system, basically the compressor or the pump charges the receiver, just the same as it does in the hydraulic system. But again, the capacity is much higher in a pneumatic system, and you can survive a longer override in case of a power failure. So the distribution system is very localized in a hydraulic system. You may have several different hydraulic systems in the same area, whereas in a pneumatic system, it's more of a centralized system. You can have a central air system with a whole bunch of takeoffs for individual workstations. Which makes pneumatics much more flexible and easier to expand on than hydraulic systems. The capital cost as well is lower for a pneumatic system. The parts are cheaper, it's easier to install, you need half as much piping for return lines. And the downside on that is your day-to-day operating costs in terms of energy is going to be higher, because air is compressible, and the more you use, the more you have to generate. So generally, your cost of electricity is higher with a pneumatic system. And in terms of the different types of actuators, in linear actuators or cylinders, you have a much higher force in hydraulics than you will ever get in pneumatics, because you can compress a gas, but you cannot compress a fluid very much. As a result of that, what goes out of the pump is basically seen by the linear actuator, minus line losses, of course. In rotary actuators, they're low speed on a hydraulic system, but they have excellent torque and good control. And in a rotary actuator, it's basically all or nothing, because of the fact that the fluid is compressed. So I need to get that head of steam or that inertia. So basically, if I'm looking for a very high speed motor with not a varying load, a pneumatic system is better than a hydraulic system, depending, of course, on the power consumption. So in terms of the fluids, both of them are a fluid, except that one uses a gas in a pneumatic system, and that means that it's compressible. Hydraulic systems are able to generate much higher forces, upwards of 700 bar or 700 atmospheric pressures, 7,000 kPa. Whereas pneumatic systems are generally between 5 to 10 bar. Tools and processes such as like that. Positioning, excellent for mechatronics because it's clean. Hydraulic system, of course, is a closed system. The fluid is returned to the reservoir. The fluid is contained within the system, whereas in a pneumatic system, it's an open system. Once the gas is used, it's vented out to atmosphere. The result of that is if I have a leakage in my pneumatic system, it doesn't affect the system as much as a hydraulic system leak, which can be catastrophic, as well as very dangerous. Air leaking out at high pressure, other than getting whipped, it's probably not as bad as if a hydraulic hose lets go. That would be much more egregious. So valve operations, in terms of operating the valves and the piping and plumbing that go to them, are much more difficult in a hydraulic system because you must take that fluid back to the tank. And in a pneumatic system, it's vented to atmosphere. So have as much piping, easier to set up valves, and also much lighter too. Hydraulic system is a fraction of the weight as a hydraulic system. The hoses don't have to supply as much pressure, therefore they're thinner. The medium that it's pumping air is much lighter than the fluid, and they're much easier to deal with. So a light system with quick response. And we're dealing with pumps versus compressors. The pumps are for pressurized liquids. Compressors, of course, compress the gas into a receiver. So the compressor takes a little bit of air at a time, compresses it, and dumps it into the receiver, whereas a pump, of course, will move the fluid in an uninterrupted chain, as it were. In hydraulic systems, the fluid itself is a lubricant, so there's no need to have additional lubrication. In an air system or pneumatic system, that is a requirement for your valves and your tools, so that they don't wear seals away and have performance reduction due to leaking. So the logic symbols are fairly similar between the two, the schematic symbols. The big key difference is in a pneumatic system, the triangles are not filled in a hydraulic system. They are filled in. If you take a look at the left-hand diagram there under rotary actuators, you'll see the difference between both a fixed displacement and a variable displacement hydraulic motor and pneumatic motor. And of course, the arrow through it means that you have a variability there. If there's no arrow, that means it's constant. So that's something to look for. On the right-hand diagram there, we have various hydraulic schematic symbols. If they were pneumatic symbols, they would just not be shaded in. And we're looking at their 2-position valves and 3-position valves. If I can direct your attention to the center position, which is going to determine, well, the center position is going to be determined as to what you're going to use. For instance, if you're using a closed center, an open shared center where all 4 of the valves are connected together, so the pressure is equalized no matter where it is in the system, and the second one down on the right-hand side, or you have the regenerative center position, which we simulated in the lab by using the manifolds, if you remember. I pointed that out. And of course, below we have restrictions, flow controls. We have variable flow control, static flow control, and then we have a flow control that's variable with a check valve. And again, the very bottom last one there, schematic symbol, is that of a pressure reducing valve. Okay, so if the pressure gets too high, the arrow will go to allow fluid out of the system to drop the pressure down to the preset. So actuators or linear actuators are basically very similar in a hydraulic and a pneumatic system. There really isn't much difference. So a differential cylinder on the top right-hand side, an area of 2 to 1, which means you're going to have twice the force on the cap end as you're going to have on the annular end. The synchronous cylinder means that it has the same pressure gradient either way. That cylinder would be used for positioning in either direction. It's used as a steering cylinder on pieces of equipment, mobile equipment, as well as to push and pull gates on conveyor systems. And we also have cylinders with cushioning on there, and that's a variable cushion because the arrow is going through it. And the cushion is designed, remember, to slow the end position. So as the cylinder comes to an end position, it doesn't have a big full stop. It coasts to a stop at the end, which is very useful. Now, on the left-hand side diagram, we have the different types of linear actuator mounting systems, depending on whether or not the actuator is going to be deploying an arc or a straight force. So an arc would be if it's on an elbow joint on an excavator, as opposed to pushing a linear rod. And how I mount the cylinder is going to be determined by the work it will do. So that's important. So all of the common types of mounting are illustrated there. And you will see different applications depending on what kind of system that they're being put to use on. Hydraulic fluid. Of course, when we talk about pneumatic fluid, we're talking about atmospheric air, which is basically filtered and has the water taken out of it. But a hydraulic fluid is a very scientifically designed lubricant. And, you know, here we have Sinopec specs for their hydraulic fluid. Comparing to other manufacturers such as Chevron, Mobil, and Shell. And you see the viscosity is 46. And the viscosity has a definite thickness at a perceived temperature. And you see there that the viscosity is at 40 degrees C, right? And therefore 40 degrees C, it's said to have viscosity at 46. Its viscosity index 165 versus 143. So higher viscosity index means that it is more constant across the temperature spectrum. Flash points, all basically the same. Some are a little bit higher, 216 degrees centigrade versus 225 or 232 in the case of the Mobil. And the pour point, if you're looking at the pour point in terms of how cold can it be before it will no longer pour out, and minus 47 for the Chevron versus minus 39, I'll be honest with you, who's going to be wanting to I'm not going to be handling hydraulic fluid when it's minus 40 unless I really, really, really have to. Now, I did work in a mine in northern Alberta that had a lot of hydraulic equipment, and the hydraulic systems in there, if they were kaput or no good, we would bring them back into the shop. There's no way that you would try and pour oil or try and run a system from a cold start at minus 30. The temperatures that we would experience in northern Alberta would be very much around that minus 40 mark in January and February. So anytime we were using oil, it would be pre-warmed. It would be bringing it out of a nice warm shed to put it into the system. There's also other things you want to look at in terms of your hydraulic fluid. Is it hydrophobic? In other words, does it shed water? How is it at conducting heat? Does it foam? And what kind of oxidation does it have? Does it oxidize your components? And remember that it's very critical that your fluid match your seals in your system, and you don't want to substitute hydraulic fluids unless you get permission from the manufacturer of the equipment. You can damage some seals by putting in synthetic fluids if they're designed for mineral oil based. Or if you're using some kind of a glycol-based fluid, you can't substitute mineral oil in that unless it has the same properties because otherwise you will just damage the equipment on that. So that's very important that you know what type of fluid you have. Very much like people. I mean, you wouldn't put type O blood into somebody who has type A blood. is you'd end up killing them. So it's very important that your fluid matches your system. In a pneumatic system, of course, we don't have that problem. Air is air is air, right? You may have to have different criteria in terms of your your pneumatic air in terms of moisture content or lubrication, but generally you're not worried about things like viscosity. Of course, in a pneumatic system, viscosity isn't your problem because you're compressing the fluid. Filters and reservoirs. On a reservoir on a hydraulic system, it does way more than a reservoir on a pneumatic system. A reservoir on a pneumatic system basically is just a big air tank. It does have a drain on it to remove some of the water that may precipitate out of the system as it comes to rest in the reservoir. But compared to a hydraulic reservoir, which is designed to defoam the fluid, allow contaminants to settle to the bottom, shed air and gases out of the system, and also remove heat. The reservoir in a hydraulic system is much busier than a reservoir in a pneumatic system. As so, the filtering on a pneumatic system is literally the inlet filter to keep the compressor from being damaged, and then generally point of use filters from there on. So I would have a small filter at each machine in my pneumatic system, whereas in my hydraulic system, I would have a filter on the return side and probably a filter or a screen before I get the inlet to the pump. And there you see on the top right-hand corner and in the middle there, the different types of filters that are available. Some of them are screw-on, very much like the oil filter on a car, and some of them are cartridge filters that go inside a sleeve and a cap, depending on where they are in the system and the system's design. A smaller system will have the screw-on type that you see in the top right-hand corner, where larger systems will have filter elements, which are a little bit more expensive and more specialty. So some of the things that we looked at in the lab, if I have a hydraulic fluid or for that matter, a gas that I have under compression, I need a way to control it and send it places. So the first thing I'm going to do is I'm going to set the pressure at which that fluid is running at, and that can be done by using a pressure reduction valve. And in a pneumatic system, that's generally done at the point of use. I will have a system pressure valve that is in the reservoir to prevent an overpressure situation, and a check valve in the reservoir to prevent the air from leaking out back through the compressor. However, the system air in the plant to 100 psi, or approximately 10 bar. And at the point of utilization, I might only be using 3 bar in the machine that I'm using. So I can dial that pressure down. Basically, in a centralized loop, I would have the pressure on my pneumatic system cranked above the largest or the highest pressure required in the system, and I would dial down all of the other drops for individual machines from that high pressure feed. Hydraulic fluid system, totally different scenario. I may have a system pressure reduction for a particular cylinder, but not usually for the entire process. The pressure reduction valve would be designed so that we have a uniform pressure and we're not wasting energy by adding motion to the fluid, or adding, in our case, adding power to the hydraulic fluid and then not using it and dumping it directly to tank. I mean, that's pointless. So you want to make sure that the system pressure that you're operating at is what your pump is providing. Next in line, of course, we have a directional control valve. The picture at the top in the middle there shows the directional control valve for a hydraulic system in clear plastic, so you can see the inner workings of it. Very similar with a pneumatic system, except in a pneumatic system, of course, the directional control valve doesn't go back to tank, it just vents to atmosphere. And here below, you'll see that that is a 3-position, 4-way directional control valve that's solenoid operated on both sides and spring return to the center position, and it's a closed center position. So of course, those particular actuators, linear or now, I wouldn't use this particular one on a rotary actuator because that motor would come to a dead stop as soon as I hit the stop switch. And that can be very hard on the motor. I want it to coast to a stop, which would be better. So I would use a regen center or an open center for some kind of a rotary actuator. A linear actuator for like a front end loader or excavator would be the closed center type that we have here. Finally, in a hydraulic system, if I'm going to control for speed, I'm going to control the flow. And that's a simple flow control system there with a check valve that makes sure that we only have it in one direction, as opposed to having it in the flow in 2 directions controlled. That's generally how we're going to use them. Is in that kind of configuration. So we're controlling in one direction. In the lab, if you remember, we could control the extension speed and have the retraction speed at a set speed. And if you wanted to control in both directions, you could use 2 control valves, or you could control the feed on the pump. There's another way of doing the same thing. Okay. Seals. We covered seals and all different types of seals and what they do. And for instance, here is an example of a cylinder, a linear actuator, and there's various different seals on there. I mean, we have the guide ring, which keeps that cap centered inside the piston and prevents the wall from becoming scratched. It's usually made out of PTFE or a Teflon, and our piston seal itself is probably some kind of an O-ring or a butyl rubber. There's a static seal there on the piston itself where it connects to the rod to prevent fluid from going up the middle there. And on the annular side, we have, again, another rod guide to make sure that rod goes in and out smoothly, and that may be made out of brass or a Teflon again. A rod seal, which seals the rod, so as the rod extends and retracts, we don't lose fluid out or take contaminants in. And then finally, on the far right-hand side there, you are going to have a wiper seal. And that seal is designed to make sure that we don't draw contaminants back into the system. You may also have a rubber boot that goes on top of that, an accordion boot, and that will keep the system totally clean and that rod pristine. And you'll find those, I bet, different types of equipment, especially mobile equipment working in dirty environments to try and keep the system clean. And it's very important that those systems be kept clean. Otherwise, the contaminants getting into the hydraulic system can ruin pumps, directional control valves, flow control valves. Because remember, inside your hydraulic system, even though it may be a 1/2-inch line going to that cylinder, there are teeny tiny little passages that are not very large that the fluid has to go through. Now, rotary action actuators or motors, depending, of course, on what kind of an application you have. Pardon me. And these are all examples of rotary action motors. We have a pump on the middle there, but a pump and a motor are basically the same, except for one is going to take mechanical energy and turn it into fluid energy. The other one is going to take fluid energy and turn it into mechanical energy. On the right-hand side there, we have an example of radial pumps. But again, the pumps and the motors are very similar in the way that they work. So gears, vanes, and rotary pistons are the biggest types of systems that are used for pumps. In a pneumatic system, a vane motor is the way that's used quite commonly because the vane motor is good at speed and torque control over a variety of speeds. But remember that in a pneumatic system, you're going for speed because a pneumatic motor can develop way more speed than either an electrical system or a hydraulic system, unless you're adding expensive equipment such as frequency drives and whatnot. Okay. And that's basically it in a nutshell. There are some review questions in there for you to take a look at. And the exam, I haven't been too hard on you. Basically, anything that you are going to be doing in terms of hydraulics or pneumatics, the logic symbols and the schematics are going to be very important for you to use for troubleshooting a system. Knowing the basics on how a system works and the requirements is going to give you a great leg up when you go to maintain or install a system. If you're going on to the design end, I mean, this is just a bare bones introduction because you'll be going much deeper into it and much deeper into the math too in order to calculate the size of actuators and pumps that you're going to require and the types of directional control valves. Anyway, I've enjoyed my time with you and I appreciate the opportunity, and I really do look forward to seeing you in person again in the years to come. And thank you very much for your time and attention, and have a great day.